Hi, today we are going to determine the electrical field of an infinitely long straight line charge of uniform density rho Sabal in air. Okay, due to solve this problem, we are going to take the advantage of Coulomb's law, which is manifested right here. We know that Coulomb's law is stating that we can determine the electrical field at any point in free space or in air if we know the magnitude of charge that is causing this electrical field and the distance between the point and the electrical field. And let's start demonstration by drawing this infinite long straight line of charge. And in our case, we will consider that this charge is directing toward z prime direction. And the reason behind using z primed that we want to remove the ambiguity as we represent the coordinates of the line charge with a prime notation and the coordinates for the point without a prime. From this long straight line, I'm going to take a small differential piece of path. I will call this small piece by d z prime. And I want to determine the electrical field due to this point. So I'm going to draw a straight line between this differential path and the point P. Okay. Now we know that the electrical field is going to be this is the point P. The electrical field is going to be along this line, which is toward a r direction. Also, this is r vector. Okay, as this piece of line is differential, so the electrical field due to this is differential to dE. Okay, now let's write dE is toward AR. The charge is equal to the charge density rho Sabal, or the charge per unit path, times the length of this path, which is dz prime. So this is rho L dz primed divided by 4 pi epsilon, and the distance is r squared. Okay. For the most of times, it's so hard to determine this unit vector, so it's preferred to write it without this unit vector. We know that this vector r consists of a product of unit vector a sub r times the modulus of this vector, which is r without the bar above. So this could be written using this form. Anyways, this form of equation is not preferred, so it's more preferred to find a better version of equation, since this problem has a cylindrical symmetry, or by other words, this line is going to affect the space by a uniform type of electrical field. The electrical field around this line is not going to have any preference. It's going to be identical in all at the whole space around this line. So the electrical field around this line is going to be something like this. You see, this hypothetical cylinder represents the electrical field around this charged line. So we are going to use the cylindrical coordinates instead of the spherical coordinate system. In order to solve, just assume that this point P exists on the surface of this hypothetical cylinder, which represents the field around this line charge. Okay, firstly, this r vector this R vector, as we see, is a summation of two vectors. According to tip to tail, is the summation of this downward vertical vector and this vector of directing rightward. Okay, this vector, this R vector is equal to this minus this Z prime vector. This vector, which is representing, this vector has the length of the arbitrary distance between this small differential piece of charge and the origin, and it's directing downward. So it's directing along AZ, along minus AZ direction. So R vector is equal to minus AZ, which is the unit vector, times the magnitude or the modulus of this vector, which is 0 prime. Okay, now plus this vector, as we see, as I aforementioned, assume that this point exists on the outer surface of this hypothetical sphere. Okay, so this vector is representing the radius of this sphere. Okay, this is R vector, a small lowercase R vector. A sub R, which is the unit vector, and its modulus is R. Now, substitute this R vector magnitude into this equation. Okay, I forgot. The modulus of this vector R can be calculated using Pythagoras equation. You know that R is the hypotenuse of this triangle. So R is equal to the square root of the square of Z plus the square of R. Now substitute these two formulas inside this equation, and we will have it's apparent that this vector is a summation of two components. So this is equal to two components, can be written using this form. Now each component of these can be written separately from the other component. And the other component could be written like this. I'm sorry, I forgot this D. As we see, this is the differential electrical field, or the electrical field for this small piece of the line charge that we have showed before. In order to find the electrical field along this whole line, we are going to integrate for both sides. Okay, I will start with integration of this component of the electrical field at Z direction. Okay, we will integrate for this side, and the answer of this is so easy. It's E sub Z. Now let's integrate for this side. These all are constants, and for this we are going to integrate along this line, as this line is infinite. So the integration is going to be between infinity and minus infinity. Okay, before start this integration, I'm going to rewrite these constants down there. Now to solve this, I'm going to substitute infinity and minus infinity with the constant alpha, then I will take the limit for alpha tends to infinity, like this. Limit alpha tends to infinity. And the integration is going to be between alpha and minus alpha. Okay, we are going to solve this by substitution. Okay, I'm going to take this variable, this new variable delta. I will make this, I will equalize delta to. Now, take the first order differentiation for both sides. Now, let's reset the limits. It was between alpha and minus alpha for the integration with respect to z. Now the range with respect to delta is in the following formula. If they can be found by substituting alpha and minus alpha in this equation, and the answer is. Now let's rewrite this with the new settings. And we know from calculus that the closed integration is equal to 0. So the electrical field at z direction is equal to 0. Now the integration, now we will do the same procedure we did before. We will take the integration between infinity and minus infinity. Now, in order to solve this, okay, so in order to solve this, we are going to use the substitution. I am going now to set z to be equal to r tangent of u. Now I'm going to take the first order differentiation for both sides. Okay, now let's set the range of the integral. As I did before, I substituted infinity for alpha, and then I make alpha tends to infinity. Now, to find the value of u, the value of u is equal to the arctangent of z over r. Now the limits are going to be, in order to avoid rewriting this big term over and over, I am going to equalize this for beta and equalize this for minus beta. Okay, now let's add all of these adjustments to this limit, and the answer is going to be. Now I am going to take r squared as a common factor from the denominator, and r over r squared and r squared, and when we raise r squared to the power of 3 over 2, the answer is going to be r cubed, and r over r cubed is 1 over r squared, and we will lift with 1 plus tangent of squared u, and we know from trigonometry that 1 plus the squared tangent is equal to b secant squared. And secant squared, when we raise secant squared to this power, we will end up with secant cubed. And the answer is going to be, and after these simplifications, this limit will be end up with, I'm going to rewrite the simplified version down there. cosine u, as we know that secant squared over secant cubed is 1 over secant, and the reciprocal of the secant is the cosine. Now take the integration, and as this constant, I'm going to add this to this, and we will end up with, I'm going to substitute beta for its original value. And forgive me, I forgot to write this limit. Okay, so I will add it up there, this limit alpha approaches infinity. Okay, now this is going to be, no, this there's minus over down there. Okay, now we are going to substitute u for these two values, and the answer is going to be like this. I'm going to write it on another paper. Okay, now you may have this question. What does sine of arctangent of alpha over r equals? Now, let's take arctangent of alpha over r. Okay, this, let's equalize this to theta. Okay, now, it's so easy to find that alpha over r is equal to the tangent of theta, as arctangent is the inverse of tangent, if you don't know. Okay, now from trigonometry, we know that the tangent, let's assume that theta is equal to this. We know that the tangent is equal to the opposite, which is in this case it's alpha, divided by the adjacent, which is r, and the hypotenuse in this case is equal to the square root of the summation of the square of alpha and the square of r. Okay, now we said that we want to find sine of the arctangent, sine for the arctangent alpha over r. Okay, which is the sine of theta. Okay, the sine of theta in this case is the opposite times the hypotenuse, which is alpha over. Okay, now let's substitute this. Now substitute this for this term, and the answer is going to be, okay. Now this is could be written. Now we can multiply the numerator and the denominator by 1 over alpha, and which is the greatest power of alpha over there. Okay, and the answer is going to be, let's take 2 out of this, and this is going to turn to 2, as 2 over 4 is 1 over 2. This is going to be turned into 2. Okay, limit, and when we substitute alpha for infinity, or make alpha tends to infinity, this term is going to be 0, and 1 over 1 is 1. So the answer is going to, so this all is going to be 1, and the answer is going to be, now this is too much gray, and according to this we found that this equals 0, and this equals this term. So according to this equation, d sub e is equal to the unit vector a sub r times, and that's the end. See you in another video.